Welcome. In this video I'll discuss plasma resistivity and go through a derivation in a simpler form to get a result which is pretty close to the full derivation. So in order to do this, I'll show how you need a linearized collision operator from the kinetic equation. There's a particularly simple form of this called the Lorentz Operator, which is where you assume the ions have an infinite mass, and then you're just looking at the electron collisions with the ions, and then going to look at how you solve this using Legendre polynomials. This is a pretty standard form, or at least trick, for doing this, because the operator has simple solutions in Legendre polynomials. And we'll look at the solution we get, and then I'll try and explain how it's different from the full solution. And so the paper that all this relies on, the full derivation was done, is by Spitzer and Ham in the 1950s, and this is the reference. So this is a 1953 paper in Physics Review, volume 89, and the formula is what we all use in things like the plasma formulary or the standard textbooks. You'll find the expression for the resistivity, and it's a slightly horrible expression, but most of it comes from the collision frequency or collision time for the electrons. So we have things like the mass terms. We have this log lambda, which is a Coulomb logarithm, which is sort of around 10 to 20, but around this kind of 16 kind of region. But this is a logarithm, and it's not very sensitive to changes in density and temperature, so it's not generally a big problem. And then most of these terms say things like the Z. This is the ion charge, so it's coming from the electron ion collision time. And then we have the temperature. The units, this you'll see different places. So I've put the factor of E here, because if this is an EV, then E times T gets in joules. You'll quite often see this written as KB, so the Boltzmann constant times T, and that's if T is in Kelvin. Or sometimes some authors just write this as T and assume it's in energy units, so it's basically in joules. So this is in T in EV. The important thing to note is that the temperature is on the bottom, and so as temperature goes up, the resistivity goes down. And this is connected to the fact that the velocity, as the velocity goes up, the collision rate goes down. So we'll come back to this a few times in the talk, because this is quite an unusual feature of plasmas, but quite important, that the faster the particles move, the less often they collide, and so here the hotter the plasma gets, the less resistivity it has. And so in general, what we're looking for when calculating resistivity is a linear relationship between the electric field and the current. So in general, you want something which has this kind of electric field. It's eta times J, where eta may in general be a tensor. So we might have a tensor relationship, but at least it's a linear relationship between the current and the electric field. And so we'll look at how you get this. And here we're starting from the kinetic equation. So this is the Vlasov equation plus collisions. And this is for the electrons. So we have a term here. We have the electron charge, electron mass. So if I mess up the E accent here, it means electron mass. These V's are the kinetic velocities. This is a coordinate velocity. So this is the velocity coordinate, which is different from the U, which is the fluid velocities. These are all kinetic velocities. This is the collision operator, which in general depends on the electron distribution function F, but also on the ion distribution function too, which I just haven't put the other parameters in. And so Fe here is the electron distribution function, which depends on time, space, and velocity dimensions. So what we can consider is that on long time scales, so we have a continuous constant electric field. We're looking at time scales where the electrons have time to reach some kind of equilibrium. And we can assume essentially that these terms, the time derivative term has gone to zero, this term has become small, so it's a large length scale, so the gradients become small. And we can consider essentially that it becomes a balance between the electric field and the collision term here. So these two terms become most important, particularly if we include or look at cases parallel to the electric field, to the magnetic field. Then we essentially just have these two terms which balance each other. If you look at long time scales, that's gone. Long length scales, that's gone because it has a gradient. And if it's long the field, then that term is also gone. And so then let's put this here. And now from this equation, we can work out the current. So the current J. So because it's electrons, we've got minus E, and it's the flow velocity of the electron. So we take the distribution function, multiply by V to get the average velocity, integrate it over all three velocity dimensions, and then multiply by minus E would give the current. And so you could essentially apply this to this equation to work out the current. And then in here we have the electric field, so you work out the electric field. Unfortunately, in general, this gives a nonlinear relationship. So here we have a term we have gradients in velocity here, which bring out a couple of terms here. This collision operator is in general nonlinear, and so this will give you a nonlinear equation. Okay, so instead we have to do something a bit more clever. We have to look at what is balancing in this term here. So if I call this equation 1. So in this equation, obviously the left-hand side is balancing the right-hand side. What is it about these terms which is balancing? So we can just do an order of magnitude estimates, and so we say that on the right-hand side, the collision function, so CE of FE, is roughly like the distribution function times the collision rate, so nu E. So it's the collision rate times the distribution function. On the left-hand side, we have minus E over M. We have a particular E field here. We'll come back and label. And then this gradient, we just say this order of magnitude, this is just distribution function divided by typical velocity. So this is like F E over V. And then a typical velocity is the thermal speed, so VTE. So it's the thermal speed. So we have this is roughly equal to this collision operator, so F E times the collision rate. And this we can rearrange. See here the F's cancel, and so this gives an expression for E. And this we're going to label ER for reasons that will become clear shortly. And this is just given by essentially multiplying this out. So this is the electron mass. So it's ME times the V thermal speed times collision rate divided by E. So this is a typical electric field, and what's happening in this electric field is this is the field you need to balance the collisions against the acceleration of the electrons. Now what happens if the electric field is larger than this is quite interesting. So if the electric field is bigger than ER, then the electrons accelerate, so the acceleration term is bigger than the collision term. And as the electrons get faster, the collision rate drops. So nu E goes down as the velocity goes up. And so as the velocity goes down, the acceleration becomes even larger. And so the velocity builds up and up and up, and the electrons are accelerated. And this is called a runaway. Because as the electrons accelerate, the collisions go down. The collisions go down, the electrons can accelerate even further. And this runaway acceleration is just called a runaway or slide away. Slight variations, but essentially this is a runaway process. Which leads to the generation of very high energy electrons. This can be dangerous during things like disruptions. So where you can get a large electric field which exceeds this breakdown runaway limit, and then you get a large population of high energy electrons which can be generated and then damage parts of the wall if they hit them. So there's a runaway field if E is bigger than ER, and in particular fluid models break down. So if we're trying to use a fluid model to model the electrons, then at this point, if the electric field is bigger than this, then the fluid model is no longer valid. And so what we have to assume, so we're assuming that now that the electric field is much less than the runaway field, and so the electron collisions are pushing the electrons back to Maxwellian, and we don't have this runaway process, and therefore we can use a fluid model. And this is a small parameter, so E over ER is a small parameter. So this is just going to call this epsilon. This is a small parameter. And what this allows us to do is then to look at this equation again. So if you have a look at this term here, so now E is essentially small. This is a small parameter here, and so this whole term is going to be balanced by terms in here. And what we're going to do is we're going to essentially make F a perturbation, a power series. And so we're going to have a low order F, which is essentially Maxwellian, and then first order F, which is the same order as this small electric field. And so there's a small perturbation to F is balanced by a small electric field. Write this out here a bit more. So there's a perturbation expansion. So just writing down Fe is Fe naught, which is a lowest order, so first order in that, plus Fe1, and which is smaller than Fe naught by this factor epsilon, plus Fe2, plus so on. So we're only going to go to first order, but in principle we have a power series. Each order is order epsilon smaller than the previous one. And so what we can do is you write down the equation in orders. And so the 0th order, well, to 0th order we have this Fe0, and so on the left hand side we have 0, because this whole left hand side is first order because it has this electric field in, and on the right hand side we have the collisions Fe0. So this just says that the lowest order distribution function obeys this, and by the H theorem, this is Fe0 is the Maxwellian. And so we just write down what Fe0 is. So here U is the fluid velocity, so it's the average velocity of the electrons. V is the kinetic velocity, and so there's a Maxwellian distribution with a width, a characteristic width, which is the thermal speed. Because then we go to the first order in this equation, and then of course we pick up the electric field. And so now on the left hand side we have the first order term, which is the electric field. There's an F0, so this is like Fe0, it should be the 0th order term. If we had first order here, then this would be a second order term, so here we just have Fe0. And on the right hand side here we have the first order term Fe1 here. And so now we have an equation for the perturbed distribution function Fe1 in terms of the equilibrium distribution function, which we know is Maxwellian, and the electric field. And so this is now getting something where this is going to look like a function of the current. This is obviously linear in the electric field, and this is turning into something which could be the Ohm's law. And because we know what the form of this is, so we can just take this Maxwellian and put this into this function here, and then we end up with, we can basically take the derivative with respect to velocity of this equation, and we end up with this. So we have the collision operator on the first order distribution function, and on the right hand side we have this. So we have an E dot V and the equilibrium distribution function. The problem now is how to invert this, because in general this operator is a quite difficult thing to invert, and the full Spitzer-Hahn calculation is quite involved, because this collision operator, CE, here written as the first order distribution function, in general is a function of collisions with the electrons and ions, so it's CEI. So it's due to the electron distribution function and the ion distribution function. plus the electron-electron collision as well. So this has in general electron ions and electron-electron collisions. And this is the problem which Spitz and Hum worked on or solved, is involving both of these components. For now, we're just going to make some simplifications, and so for this part here, we're going to assume that the ion mass goes to infinity. This is the Lorentz limit of the Lorentz collision operator is from this. And then this part here you can then linearize. So this part here is first linearized. So this becomes basically TEE. So you assume that essentially you have the electron background colliding with the perturbed distribution function plus the perturbed distribution function colliding with the background. So E naught. So this is a linearized operator, so which is assuming that this perturbation is small compared to the background. In our case, we're then going to neglect this part entirely, so we're just only going to include the Lorentz part, the electron ion collisions. In principle, you can include this, it just becomes much more complicated. And so I'm just going to illustrate this. So we're only going to consider this electron ion collisions, and we're only going to consider this Lorentz form of it. Okay, so now we have say an electric field like this. So this is E. And then have a velocity vector v. This is the velocity of the particles. The angle between these is going to be theta. It's the angle between the velocity and the electric field. And then we have another angle. To draw this is basically the angle. You can rotate this arrow around here. So this angle here is called phi. As you move to the angle, it's phi, and this theta is the pitch angle. So it's the angle of the motion with respect to the electric fields. It's quite often useful to write this in terms of cos thetas, because the dot product E dot v, which appears in this equation up here. So here we have an E dot v term here, so it's the component of the electric fields along the velocity. This is of course just has a cos theta. So it's E times v times cos theta. And this cos theta, we're just going to label mu. It's the pitch angle variable. And so using this pitch angle variable mu, we can write our equation, this equation here. Using this Lorentz form of the collision operator, we can write this equation here in this form. So here on the right hand side, this is the Lorentz collision operator in terms of this mu parameter for the pitch angle. And now one thing is that this left hand side doesn't depend on phi, the azimuth angle, independent of phi. And so hence this whole right hand side must be also independent of phi. And so we're not differentiating phi here. And so FE1 must be also independent of phi. And so this whole term here can also go. And now we're just left with this operator, so a second derivative in mu operating on this, which you have to invert. And now a common trick is to use Legendre polynomials to solve this equation. So we write the perturbed distribution function f1 as a function of velocity and pitch angle as the sum of a set of components labelled by L of the coefficients AL, which is just functions of v, and the Legendre polynomials labelled by L, which are a function of mu. And then using this, you can substitute this into this equation here. And now this operator operating on Legendre polynomials gives this solution. So what I have here is this term here, it just becomes essentially a number. L is just an integer essentially, times these polynomials coefficients here, times these a's. So on the left hand side you can see here that none of this depends on pitch angle. So the equilibrium distribution function doesn't depend on mu. So this is the only factor here depends on mu is this mu here. And so there's only one term in the polynomial, because you have p1, so L is 1 of mu is equal to mu, and so this cost balances this mu here, and so therefore you only have one term, so you just have a1, which is a function of v, so some coefficient times p1, which is a function of mu, which is just the same as mu. This is equal to fe1. And so we can write down the solution in terms of fe1. So it's just minus 2 times e. You can normalize in terms of the runaway electric field, er. So we have a v over v thermal, so vte to the power 4. And that v to the power 4 has come from, let's see here, so here we have a factor of v here, and here we have a v cubed, so multiplying through by that we just get v to the 4. And here again you have a v thermal squared, gives you part of here, and here you have v thermal. One of those goes into the ER, and these three, and one of these goes into becoming a v te to the 4. And so I end up with this expression here. So the distribution function is like the fourth power of the velocity times the equilibrium field. And so you can see that this becomes large in the tails of the distribution, and so it's heavily weighted towards the tails of the distribution function. If you now use this distribution function, take the integral, you can calculate the current, and you get that J is this expression here. And so therefore if you write this in terms of the resistivity, so you can call eta and eta L for Lorentz form, or the Lorentz collision operator, and you just have root pi over 8 from this part here. It's just going from the integral, and this you can compare to the Spitzer-Hahn version, so the eta Spitzer-Hahn that we had at the beginning. So if you take out the factors of nu ei, you get this. So it's actually the same, or at least the form is the same as the Lorentz operator that Lorentz resistivity we've derived. The only difference is this coefficient at the front, which is actually larger by a factor of nearly 2 compared to the Lorentz factor. So it's a factor of 1.7, around 1.7 larger. So the Spitzer resistivity is larger. And so this is what happens when you include the electron collisions. So when you include the electron collisions, which the Spitzer-Hahn calculation does, then this pushes the perturbed distribution function towards Maxwellian, and it's the tails of the distribution function that get squashed to lower velocities. And since the velocity is smaller, the average collision rate goes up, and so the resistivity is increased. And this is because the velocity, so the collision rates, so nu ei goes roughly like 1 over the velocity cubed, and so by decreasing the average velocity, you increase the collision rate.